examples of modified gravity theories that historically have been really important. And that was scalar tensor gravity, F of R gravity, DGP gravity. And then at the end, we saw all of those kind of scalar tensor type theories could really be summarized in this kind of uber theory, which was Horndeski gravity. And then we started doing just a little bit of linear perturbation theory to kind of see that if we had a modified gravity theory that changes the Poisson equation, that's going to change how density fluctuations in the universe grow with time. And what we're going to do today is we're actually going to start on a little bit of a fresh slate, which is we'll start by talking about gravitational waves. And this first lecture will be about how gravitational waves come into this picture of testing gravity. And then after the break, we'll kind of pick up that Horndeski framework again and go back to talking about the sort of large scale structure constraints on that sort of family of gravity theories. Okay, before we get cracking, I just wanted to bring back again this slide from yesterday. So this was the kind of mental map of the sort of tree we go down with a modified gravity model. So we spent most of yesterday looking at the Lagrangians, and in a few cases, we were deriving from those the field equations and the equations of motion for the scalar field, for example. And we did a little bit of this as well. We sort of looked at the background solutions that describe the expansion rate of the universe. And we just started going down this kind of arm doing linear theory. Today we're going to start by going down the other arm instead. So if you do perturbation theory, but you look at the spin 2 parts of your perturbations, that gets you to a description of gravitational waves. Okay, so here we go. Gravitational waves as a probe of cosmological gravity. So first of all, I need to make an important distinction between two kind of phases of a gravitational wave's life, which is the generation and the propagation phases. So gravitational waves in principle, of course, are born in a strong field regime. So you know they're produced by the merger of compact objects like neutron stars and black holes. And of course, the space-time is very highly curved around those objects. So that's gravitational wave generation. And there are modified theories of gravity that would really come out, so would really show themselves in those really strongly curved, strong field environments. However, if you recall our discussion yesterday where we had that plot with lots of different gravitational systems and we spoke about the curvature scale on the y-axis, in cosmology, really the problems we're trying to tackle are in the low curvature regime of the plot. And you can think of that as being actually a weak field regime. So what we're really interested in is what happens to a gravitational wave once it's left its source and it travels across the large-scale structure of the universe. So this is the gravitational wave propagation phase. And today I'm going to focus just on that propagation phase. I will not consider modifications to GR in the strong field regime. That's somebody else's talk. And the reason I'm sort of allowed to do that will be due to a property called screening, which we'll talk about a little bit after the break. So for now, just take it, the gravitational waves are produced in GR, and we're going to ask what happens next as they travel across the universe. Okay, so we want the gravitational wave propagation equation. So once your gravitational wave has got out its host galaxy, it's kind of got clear of that, its propagation across large scales is described by this equation here. Okay, box acting on h mu nu, where h mu nu is our small spin 2 perturbation of the metric tensor of space-time. And if we can expand this, the left-hand side of this equation on an FRW background, so a smooth expanding universe, it looks a bit like this. Okay, so it's a wave equation. Right? It's got a second order time derivative. And in my units, a prime will be a derivative with respect to conformal time. And so this curly h is the conformal Hubble factor. second order time derivative, second order spatial derivative. Okay. Um, and it's actually not just a wave equation, but it's kind of a damped wave equation. Because there's a friction term here. That's what we would sort of interpret the term in the middle as in a sort of classical physics setting. So that tells us somehow our waves are going to be damped, their amplitude's going to drop off as they travel. And you'll notice that the Hubble factor appears here. So that's kind of going to be related somehow into how fast the universe is expanding. I've sneakily gone to Fourier space. So I had a nabla squared here. I've replaced it by I times k. I just find it a lot easier to work in this version. And I'm not really going to worry too much about polarizations today, but kind of hidden within this object H, there are, of course, the plus and cross polarization plus and cross polarizations that Maya mentioned on Monday. Okay, and when you do that polarization decomposition, you make gauge choices, the time part of this doesn't contribute. So that's why the indices have become IJ. Okay, so this is the situation in GR, pretty straightforward. Now what I'm going to do is show you a version of this equation that has lots of different effects that could come in modified theories of gravity. Okay, so here we go. It's the same equation, but it's got a lot bigger because I've brought in 4 new terms. They're all coloured in. Now, in reality, probably one theory of modified gravity wouldn't bring in all of these terms at once. So you can think of this as a kind of like placeholder equation just to show everything. So what's going on? First of all, we've brought in this term, and I've just called it nu for now and indicated it's a function of redshift, that's modifying that friction term. So somehow, that's our intuition says that's kind of going to be related to that damping of the gravitational wave amplitude. That's going to be changed somehow if this new term is present. We've also brought in the possibility that our gravitational waves could travel at a speed which is different than the speed of light. Okay, so the speed of light is often set to 1 in my slides. So if you couldn't see the factors of c squared before, but you can see them now because I've written ct. T stands for tensor modes, so propagation speed of our gravitational wave. Now in GR, the graviton is massless, but again, there's a possibility in a modified theory of gravity, it acquires a mass. If you have a massive graviton, you pick up an extra term here. And on the right-hand side here, in the GR version, we had 0. Nothing sources the gravitational wave as it travels. But in some theories, like bimetric theories, where we have 2 tensor fields, actually our gravitational waves can couple to perturbations in the kind of second tensor field. So there can be a source term here on the right-hand side. And the slightly complicated structure here is just to sort of preserve the necessary index structure of this equation. So this capital gamma C is just sort of the amplitude of that source. And there's a final bit of phenomenology here, which I didn't quite want to delve into the mathematics of polarizations just because it gets a bit messy. So I've sort of slightly taken the lazy option and I'll just put it over here. So we said in GR, our gravitational wave has those 2 polarization modes, the plus and the cross. It is possible in modified theories of gravity to pick up extra polarization modes, extra degrees of freedom, like scalar breathing modes, for example. Now, I'm not going to talk about all of these bits of phenomenology in the interest of time today. I'm going to talk about 2 of them. And I'm going to talk about the 2 that are sort of most actively pursued with the current data and most sort of relevant to the story we've been telling so far, because they're the 2 that pop up in Horndeski gravity. So yesterday I showed you this beastly big action. This is the full action for Horndeski theory. Remember, we said it was the most general theory you could write down with a metric and 1 scalar field and second order equations of motion. And although it looks kind of ugly to start with, you can kind of unpack it into this stack of terms where there's something kind of like a kinetic term generalized. There's this term that we said is going to be related to screening. And then there's this sort of extension of the GR term sitting here. So GR was recovered in the limit of G4, this function just being set equal to the Planck mass squared. And finally, we sort of gave up interpreting things on the last term, which was just a big mess of derivative couplings. So what happens to this equation in Horndeski gravity? Well, what happens is that these two terms are the ones that show up. So the modified friction and the possibility of a modified propagation speed. And actually in Horndeski gravity, where I've just written this general object nu of z, that's actually related to the Horndeski G4 function. Okay, it's actually the derivative of G4 with respect to log of the scale factor. So it's basically like a time derivative. And this object I am going to call for now alpha m. And that's a little bit of cryptic notation for now. That will make sense a little bit later on in our story. So I'm just going to substitute nu for alpha m. And this thing is sort of like quantifying the run rate of the effective Planck mass, right? That's what G4 was, kind of the effective strength of gravity, but now it's changing. So that's the friction term. The speed term we will write as 1, which of course would be its GR value, the speed of light, plus some small deviation, which I will also describe with another alpha function, alpha t. Okay. And notice it's actually ct squared is set to 1 plus alpha t. Okay, so we want to try and constrain then these deviations, these bits of phenomenology. What are they going to do to the gravitational waves we're actually seeing? And the place we're going to start is with an event I'm sure Maya told you about on Monday and Tuesday, which was GW 170817, the binary neutron star merger with an electromagnetic counterpart. So here's my highly accurate diagram, highly to scale, where we've got our binary neutron stars here in the host galaxy, NGC 4993. And of course, what we received was the gravitational wave signal. And we did receive electromagnetic signals across the spectrum. But today, I'll be particularly interested in the gamma ray burst that we received from this event, because that was the first electromagnetic signal that we received. So this is a little bit of a lie because, of course, gamma rays are really detected by gamma ray space satellites, not a telescope on Earth. But we can also, we receive these two kinds of signals, and we can time the moments we received those. And what actually happened with this event is that we received these signals 1.74 seconds apart, with the merger sort of peak of the gravitational wave signal arriving first, and then the first gamma ray photons arrived just under 2 seconds later. So this is the cartoon version. Here's the slightly more scientific version. So the top and bottom panels are the gamma ray flux counts in two gamma ray spectrographs that were operating at the time, so Fermi and integral. And in the middle panel there, we've got the strain in one of the LIGO detectors. You can clearly see the chirp signal here by eye, and then it's the gap between this green line and this green line that is about 1.7 seconds. So you can use these time of arrivals to place a bound on the speed of propagation of gravitational waves relative to the speed of light. And this is quite a famous result, but I don't know how many people have actually been walked through it. So I'm going to walk you through a version of it. We're going to do the slightly cheaty version. So of course, the proper version involves computing conformal distances and things like that. But this event was so nearby in cosmic terms, you can actually get away with sort of just doing a Euclidean notion of distance, and you basically get the right answer to within sort of small values. So we're going to do the naive calculation. So what we have measured is that difference in arrival time between the photons and the gravitational waves, right? And photons arrive later, so their time is larger. So this is the correct difference. And using literally sort of high school notion of time is distance divided by speed. We can write this as the distance to the source, d, divided by the speed of the photons. I've temporarily brought that back as c gamma. I'll get rid of it again in a moment. And the speed of the gravitational waves, ct. And so I'll just pull out a factor of d divided by c gamma. That's pretty straightforward. Now, I don't like having c's floating around, so I'm going to set them all equal to 1. And we met earlier that we were going to write the ct squared as 1 plus this small deviation alpha t. So I'm going to plug in the square root of this expression. Okay, there we go. And now we said we're going to assume that alpha t is small. That's going to turn out to be a very good assumption. So we can Taylor expand this denominator here. And then pretty straightforwardly, the 1's cancel, and we're just left with this alpha t over 2. And so doing just a little bit of rearranging, finally what we get is alpha t is related to twice that time difference. And I've put back in the speed of light just to get the dimensions kind of clear, divided by the distance to the source, which was about 40 megaparsecs. So you can plug in these numbers yourself now, and if you get the units right and the factors of c in the right place, you will find that alpha t has a magnitude of about 10 to the minus 15. Okay, so it's a really, really tiny number. And that's telling us that to an accuracy of 1 part in 10 to the 15, the gravitational waves seem to be traveling at the speed of light, as would be predicted in general relativity. Probably what's going on with this 1.74 second delay, probably that is an intrinsic delay at the source, right? Probably the gamma ray photons take about 1.7 seconds to be kind of generated and released from the really, really dense mess that's left behind after a binary neutron star merger. And that's probably what causes that delay. However, I have to point out, this is only one data point, and it's one data point at really low redshift. So with one data point, we can't rule out the possibility that there's some really wild, exotic, modified gravity stuff happening at higher redshifts. And the gravitational speed of gravitational waves could be something wildly different. And as long as everything kind of looks like GR very locally, that would be consistent, at least with this data point. Now, in reality, that's probably very finely tuned. From the other gravitational wave observations, we don't see evidence that there's really crazy stuff going on. So probably we're allowed to take the straightforward interpretation that gravitational waves travel at the speed of light. Okay, so that's one part of the measurement. I'm going to come back to this speed result in a little while because there's a little bit more interesting stuff to squeeze out of this. But for now, I'll park that, come back to the propagation equation. So we've just seen that ct squared is basically 1. So let's get rid of that. And then what we're left with is this change to the friction term of our gravitational waves. What does this do to a gravitational wave that's propagating? So to dig into that, I'm going to bring back a slide from Maya's lectures earlier in the week. She very kindly shared her slides with me. Maya presented this slide where she described the amplitude of a gravitational wave. And you can see that depends on a number of things. It depends on the redshifted chirp mass, the frequency of the wave. There's a load of angular factors to do with orientation and position. But what we really care about today is this object on the denominator, which is the luminosity distance. Okay. So what we're going to do is we're going to do a sort of cheeky solution of this equation. I'm going to conveniently drop all the tensorial indices just to make my life easy. And we're going to say, let our gravitational wave amplitude h be the GR solution, whatever that is, times this factor here. So we're going to allow there to be a change of the amplitude I'll call B. And we do also have to allow for there to be a change in the phase I'll call C. So you plug this into our propagation equation. You'll get an equation with real and imaginary parts, and you can separate that into two equations. And if you solve the imaginary part, you'll find that C is 0. So actually, we don't get any change to the phase of the gravitational wave. Easy. For this other factor B, you will find this expression. So we do get a change to the amplitude, and this factor looks like an exponential, where the argument of that exponential is an integral over this object alpha m, which remember we said was like the effective rate of change of the Planck mass. Okay, so what do we do with that? So we're going to multiply that into our gravitational wave amplitude. This is my version of what was on Maya's slide, so it's exactly the same dependencies, just maybe slightly different notation in places. We've got our luminosity distance down here. I'm going to multiply this through by this capital B. And what I'm going to do is I'm going to redefine the distance in the denominator here to absorb that new factor. Okay, so there we go, where this new distance dgw has absorbed my factor, and then it's just related to the regular luminosity distance. Okay, and there's been a sign change here because this B factor was on the numerator, so when I sort of absorb it into something on the denominator, you just flip the sign. So we'll call this the gravitational wave luminosity distance. It's a bit of a mouthful, but it is the value of that distance you would infer from analysing your gravitational wave data. But what's really interesting is that that distance is now changed from the kind of normal distance it would be in GR and lambda CDM. So we can consider this ratio of luminosity distances, right? And it's now given by this object. Note that if alpha m was 0, right? So if we were in a theory of gravity like GR, where the effective Planck mass doesn't change, then you get an integral over 0. So the whole thing becomes 0, exponential of 0 is 1. So in GR, this ratio is just 1 for all times. The distances are just the same. What does it do in a modified theory of gravity? So you're going to get some non-trivial function. And although we're talking about Horndeski gravity today, this is actually quite generic behavior. So we said yesterday you could have biometric theories, theories with vector fields. They would all give you something non-trivial here. And so to plot an example of this, we need to sort of plug in some functional form for alpha m here to evaluate the integral. So rather than go to a specific theory of gravity, I could do that, but I'm going to take a sort of different and slightly more model independent approach, which is to say I'm going to have some trial function. I'm going to let alpha m be some constant I'll call Cm times this object here, where omega lambda is just the fractional energy density in the cosmological constant in a lambda CDM model. Now, the reason we do this is this object here, omega lambda divided by its value today, is a function that is very small in the early universe, where dark energy is basically irrelevant, and approaches 1 in the late time universe, where dark energy is really dominant. And that's kind of the behavior we want a modified gravity theory to have. So we're slightly cheating here. We're not deriving that behavior. We're just saying what's going to happen to our gravitational waves in a kind of generic case where we have some gravity theory that acts like dark energy. So I'm going to plug that in over here. And I've got a plot which then evaluates that. It shows you this ratio of these distances. So GR is just the grey line, just flat there. And then these coloured curves correspond to different values of this parameter here, Cm. It could be positive or negative. If it's positive, you get a ratio that's above 1. If it's negative, the ratio dips. And you can see that all of these curves kind of come together at low redshift, but they deviate increasingly at high redshift. That's going to be important. There's some sort of samples of data points on here. The only real data point is GW170817, which is the square. All these other points are just mock data from a paper I was writing. So these are sort of mock samples of other events LIGO could have observed. Of course, in reality, we haven't had any more multi-messenger events. And these black dots at high redshift are sort of mock multi-messenger events with LISA, the space-based gravitational wave detector. Okay, so we've set up this kind of friction formalism. So let's take the obvious event, GW 170817, and ask what is the bound on this friction effect from 170817? And we can do this because this object on the numerator is what we have measured from the gravitational wave signal. And because we know the redshift of 170817, we know the host galaxy, we can compute the object on the denominator, just the normal luminosity distance that you would evaluate given a redshift in an FRW cosmology. Okay, yes, sorry, I even have an expression of it there. So what is the constraint we get? And recall, we're using our sort of trial function here. So really, rather than constraining alpha m, we're just constraining this constant c. So here is a result from a paper by Lagos et al., but I think Maya is also on this paper, if I recall correctly. And what you're seeing here is the posterior distribution for that c parameter, where its value in GR would be 0. Now, there are two curves on this plot because in order to evaluate that denominator, dl, you need to assume a cosmology. And that means you need to assume a value of the Hubble constant. And of course, we have the Hubble tension, so we don't know exactly the value of h naught. So the authors here just used two different values. There's the Planck value in blue, and there's one of the local distance ladder values in green. You can see it changes the result a bit, but not dramatically. And so in either case, there's a clear peak around 0. But what's really surprising is the width of this posterior. So the two sigma bounds here are out at like plus or minus 50 for something that's supposed to be 0 in GR. That's kind of surprising, right? Compared to the speed bound we saw a minute ago, where we were constraining something to 10 to the minus 15 accuracy. It's the same event, and now we're constraining something to plus or minus 50. So why is it so weak? The reason this bound is really weak is because that distance ratio tends to 1 at low redshift, right? We saw that here. So departures from GR are tiny at low redshift. And of course, GW 170817 was like the lowest redshift event we've ever had. So it's not surprising that it can't really constrain this effect. And what we would really like to be doing instead is trying to bound this kind of friction effect with the other gravitational wave events we have. Right, so this is a plot just showing the other events in the third observing run, 03. 170817, of course, is one of these ones down in the corner. And we've got a lot of other things going up to redshift 1. So we want to use them instead. Problem is, of course, they are not events with EM counterparts, and therefore we don't have their redshifts. And remember, we needed the redshift to evaluate the denominator here. So what are we going to do? Well, luckily, again, Maya has introduced all the necessary concepts for me. We are going to use a method called dark sirens. So this is where you have a siren without an electromagnetic counterpart, and instead you use a galaxy catalogue. Okay, so just as a quick reminder from Maya's lectures, so you have for your gravitational wave event a localization area on the sky. This is the localization for 170817, so it's actually a very good one. Most events are a bit worse than this, a bit bigger. And you hope that some kind person has taken a galaxy survey in that area of the sky. And so you know where all the galaxies are, all these green crosses. And what you can do is effectively do the same analysis you would have done with a bright siren, but you marginalize over all of these possible host redshifts. Okay, you treat them all as possible hosts. And Maya showed you that surprisingly does still give you a pretty informative result, right? So she was talking about measuring the Hubble constant, where this sort of dashed pink line is what you get if you know the actual host galaxy. And if you do this marginalization procedure, you get a slightly weaker, broader result, maybe the green or the orange here, but it's still got a peak in the right place. It's still quite informative. And the beauty of this method is that, of course, whilst we only have one event with a counterpart, we've now got a couple of 100 events without counterparts. So you can actually combine those, combine constraints from those individual events and actually hopefully get something pretty informative. So this is what we're going to do. Um, I'm not going to take you through the Bayesian sort of formalism of this, A, because it becomes quite a big side story in itself, and B, I think Maya covered quite a lot of that in her lectures earlier in the week. So I'm just going to say copy paste pretty much everything that Maya said about Bayesian methods for standard sirens. But now, instead of trying to measure the Hubble constant that sits in here, we are looking at this relation, right? This is our gravitational wave luminosity distance. Here is our modified friction term. And this part over here is just the normal part. And we want to constrain alpha m, but we are going to have some important degeneracies now. Right, we can't ignore all the behavior that's still going on in the Hubble constant, for example, and all of the things Maya spoke about to do with the mass distribution of compact objects, which is unknown, the merger rate of compact objects, which is unknown. We have to include all of those parameters as well. So this turns into a really big analysis, but I will just show you the results. And in particular, I will focus on the two parameters that really matter from a kind of modified gravity point of view, which is going to be our parameter Cm sitting in here, but also the Hubble constant, right? So we're going to allow for that 2D degeneracy. So here we go. Here is the results of that dark siren analysis using events up to the end of O3. And you can see the constraint here, and it is much, much better. Right, we've bounded Cm to be 1.5 plus or minus about 2, compared to the kind of plus or minus 50 we had in the bright siren case. Okay, so we do a lot better with dark sirens than we do with bright sirens in this particular case. Okay, there is one more thing I want to squeeze out of the gravitational wave bounds arena. And it's actually going to go back to the gravitational wave propagation speed, right? So I said there was a little bit more juice to squeeze out of that. So what does that speed bound actually imply for the structure of modified gravity theories? So we're going to bring back good old Horndeski gravity. You've seen this multiple times by now. I have to apologize, on the next few slides, my color scheme is different. I try and use the same colors for the same objects throughout my talk for kind of like visual identification. In this case, I did reuse some material from a previous talk, and the colors are different, so sorry about that. Okay, so here was Horndeski gravity, and with the propagation speed, we bounded that small deviation we called alpha t. Now, I didn't tell you how alpha t was related to Horndeski gravity, but I'm telling you now. Here it is in the box down the bottom, where remember x is this kinetic term of the scalar field. There's some effective mass here, m star, which I'm not going to worry about today. But the important point is that alpha t is made up of these objects. So you can see there are derivatives of our functions g4 and g5 in here. That's what this notation means, where there's a comma and a subscript. This means the derivative of g4 with respect to x, the derivative of g5 with respect to phi, and with respect to x. And we've said alpha t has to be basically 0, or really, really tiny. So what that means is everything in this square brackets has to be 0. Now we could try and do that by arranging these terms to cancel each other out. That turns out to be really difficult and really, really sort of fine-tuned. The only sort of natural and generic way to do this is to demand that each of these three terms here individually is 0. So we set all of these derivatives identically to 0. Now, what does that mean for our Horndeski Lagrangian that's written up here? Well, let's take it piece by piece. First of all, we see that G5 subscript x, so the derivative of G5 with respect to x, that's got to be 0. Oh, sorry, I've done it in the wrong order. Sorry, we'll start with G4 then. G4 has got subscript x has got to be equal to 0. And so we've lost that part there, right? I'll just go back so we can see that. So here's the term, and that's gone. We do also have that G5 sub x is 0. I'm pretty sure this is the next piece. So that piece also vanishes. Now we look at the structure of this remaining bit of this L5 Lagrangian here, and we can do an integration by parts, because remember this is all sitting under a space-time integral in the action. So we imagine doing an integration by parts. What that will do is it will move one of these derivatives off phi, and instead it will hit this combination of G5 times the Einstein tensor. But G5 doesn't have any derivatives anymore. All right, so G5 is just a constant according to our conditions down here. So the derivative just moves through that and it hits the Einstein tensor. But that's one of the Bianchi identities. If you contract a derivative, nabla mu, with the Einstein tensor, g mu nu, that's equal to 0. So actually, under an integration by parts, this whole L5 term is going to vanish. So let's take that away. There's one more bit left to go. So we've still got this object here, G4, saying it's a function of phi and x. But actually, we've required that the derivative of G4 with respect to x is 0. So it can't have an x dependence anymore. So we take that away. Okay. So after applying all of these conditions, actually what we're left with from the original kind of big Horndeski Lagrangian is just these three pieces. Okay, so L4, L2, and L3. It looks a lot more compact and a lot simpler. Now, you might think surely this has taken away lots and lots of modified gravity theories. Well, yes, it has taken away some. There were theories called the quartic and quintic Galileons that were basically ruled out by this result. However, some things we've talked about do survive quite well. So F of R gravity, for example, fits very neatly into just these three terms. So F of R and many of the sort of simpler modified gravity theories do actually survive. Okay, that was actually what I was going to say on gravitational waves. So I know I'm slightly early, but this might be a good point to break. And if I'm slightly under on this lecture 3, I might be just a few minutes over on lecture 4. But I'm going to suggest we take the 10-minute break here.
Sounds good.
All
Thank
right.
you.
See you in 10.
All right. Well, if there are no questions, maybe we break now. Come back in 10 minutes.
Oh, sure. Yes. Sorry, I should have said I'm very happy to take questions at this point if there are some, since we're under time.
All right.
If not, I'll pick
Very
them
good.
up.
Yeah. Go ahead. One question.
Hi, Tessa. Thanks for the great talk. It just had a slight confusion. So can you go back to the slide where you showed the ratio between the luminosity distance and the gravitational wave distance? Uh,
I hate flicking back through slides, so give me
okay.
a second. Mm, mm, mm. Mm. Now, of course, I've got to share again. This one?
Yeah, this one. So here this is alpha m z, not z tilde, right? Just to confirm.
Oh, sorry, that's just a bit of that's one of the typos I warned about that could be present in the lecture. That should be z tilde. So it is an integral over alpha m over the range from you, the observer, up to the source at some distance. Redshift is an integrated quantity.
Okay. And okay, so one more thing. So you have parameterized alpha m as cm times omega lambda as a function of z divided
Hmm.
by omega lambda naught. I
Hmm.
mean, in a cosmological constant model, it's just the other thing is just one, right? Omega lambda z by omega lambda naught. Uh,
Omega lambda is, so to be clear, so omega lambda naught is the value of omega lambda today, so 0.69 or whatever, zero point 0.7. Whereas omega lambda of z is the function of omega lambda over cosmic time.
um,
So this
y-
is a function, this is a constant. And the only reason there's this normalization here is so that this ratio becomes 1 at redshift 0.
yeah, that's fine. But in a lambda CDM model, it's one always, right? Or am I?
No, no, rho lambda is 1 always.
Okay.
Energy density in the
Ah,
cosmological constant is indeed a constant. But if you compute omega lambda, which I think ends up being related to rho by a factor of h squared, I think it ends up being proportional to rho over h squared. Omega lambda is a function of redshift. That's why you have a matter-dominated era in the universe where omega m is effectively 1. Um, and then at late times, that starts to drop and omega lambda starts to rise.
right. Yeah, that makes sense. Thank you. Thank you so much.
Okay. Any more questions?
Yeah, it's on. It's on.
Hello? Yeah, when you then constrain alpha of m, like on the next couple slides,
Mhm.
um, and you have to assume your cosmology, do you have like, what we think of as dark energy there, or do you only have your modified gravity acting as uh, dark energy at late times?
Um, I'm not sure I fully unpacked the question. Let me let me say something which may or may not answer the question, and then you can tell me. Um, this is a slightly odd thing to do when you say, oh, I'm going to choose some functional form for alpha m, and I'm going to choose a functional form that depends on the lambda CDM expansion history. Because everything I said yesterday said if you change the laws of gravity, you change the expansion history. So it's not lambda CDM anymore. And so that is the correct thing to do. If you're really working with a specific theory of gravity, you start from the top, you work out the background expansion history, you work out the perturbations, blah, 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 blah. But what's sort of happening in this scenario is people are kind of cheating a little bit. They're saying, I don't know what the true theory of gravity is. All I know is its background expansion has to be pretty close to lambda CDM because all data at the moment is consistent with lambda CDM. So I'm going to assume its expansion history is very close to lambda CDM, and therefore this alpha m is sort of parameterizing sort of perturbative changes around a lambda CDM model. And I will explain that a little bit more in the second part of the talk. Is that at all related to your question?
Yes, it is.
Okay,
Thank you.
thanks.
All right, I think we have one more question here, really quick.
Hi, Tessa. Can you please go back to slide 12 for once?
Mm-hmm. Slide 12, here we are.
Yeah, I'm a bit confused here. So here we are saying that the modified propagation speed of GW is ct square 1 plus alpha t, right? And if I'm not wrong, that 1 is speed of light. So here that alpha t needs to be less than 0, right? Or else we'll be having this GW propagate faster than light.
Ah, great question. So you can have gravitational waves that travel faster than the speed of light. What is going on? So the sort of standard law that says you can't have anything traveling faster than the speed of light is kind of true in GR and in vacuum. But what has happened when you in one of these modifying gravity models is you've got this scalar field, for example, in Horndeski, that fills the universe. So it's kind of like you're not really in a true vacuum anymore. It's sort of like being in a fluid or something like that. And in that situation, the what actually defines causality is a different light cone. So you are allowed to have gravitational waves traveling faster than the speed of light in that medium of the scalar field. Does that sort of make sense? And so that's implicitly what's going on.
Oh, okay. Just a follow-up question. So in that case, will it be possible to retrieve information, or we are just redefining the causal structure of space-time altogether?
Yeah, so I believe it is the latter, so redefining the causal structure. So the kind of new fundamental limit is actually the light cone of the gravitational waves, and then the light cone of your actual photons is within that. Yeah.
Thank you.
Very good. Okay, I think that's a good time to take a 10-minute break. So we'll be back in about 10. Thank you.
Thank you.